This is the Unit 7 review, and we're looking at number 1. We want to write this in exponential form. Whatever the base is will remain the base. We're going to go across the equal sign, grab whatever value is on the opposite side. That becomes our exponent, so 3 squared, and then we're going to come back, in this case to the left, equals 9. No calculator needed. This is all you need to do. It's either going to be right or wrong. Let's look at number 2. This time we want to solve. So I'm going to write it down here. I have log of 1 over 9, 3 equals x. Now I'm going to write this again in exponential form. I'm going to take whatever the base is, and I'm going to raise it to whatever's on the opposite side. The opposite side in this case is x, and set it equal to 3. Now there's a couple different ways we could go about doing this. One is nothing about this says that we can't use a calculator. So let me show you 2 different ways. We could use mental math to do it, or we could in fact use a calculator. Let me first show you the calculator form. You would need to show your work. The reason we have logs is when you feel like you cannot solve for a variable in an exponent position, we use logs. So how do we use logs? We want to eliminate this value so that only x is on the left-hand side. So to do that, I'm going to write log of whatever this base is. It was base 1/9. So log base 1/9 goes to the left and to the right, and then I put everything else down. I have 1/9 raised to x equals 3. So this is on the left-hand side behind log base 1/9, and this is on the right-hand side behind log base 1/9. Whatever you do to the left, you must do also to the right-hand side. Okay, so I explained this in the videos that I created today that I will post on the teacher website. This exponent position, this exponent, whether it's a value, it's a variable, it pops down right in front. It's going to be multiplied by this. So I have x times this quantity, log of 1/9. And when you see this, when this value is exactly the same as this, it means 1/9 raised to what value equals 1/9. When these are exactly the same every single time, some students think it disappears, some students think it cancels out. It just simplifies to 1. So I have 1 times x, which is just x. I've recognized that more often than not, I probably did not correctly teach, and it's not that I didn't correctly teach, but I probably didn't expand on the concepts. So in the past, I would have students that got the right answer. They recognized when you had log base and these two are the same, they'd cancel out and just bring down exactly what was the exponent. So they just bring down the x in this case, and that was right, but I'm not sure they understood why. So this value comes down in front, and then this always is going to simplify to 1 when these are the same. Now on the right-hand side, I have log of 1/9 with a 3 in back. Now if we can't do that in our head, we're going to grab our calculator. Because the base is something different than 10, I can't just hit the log button. What I'm going to do is I'm going to hit math. I'm going to go up 3 spaces. And my base is 1/9 because it is a fraction. I'm going to put it into parentheses. The number behind is 3, and I get an answer of -0.5. -0.5. And we could also write that as -1/2. These are equivalent forms, whatever one you choose to do. Now, other students may be able to use mental math here. So other students, if we did not have a calculator, you're on the AP test, it's a problem, there's no calculator used, how could you do this? In that case, I would say, okay, take this value that's right now 1 over it and just write it up top. And ask yourself, what value do you need to raise 9 to in order to get 3? Well, I know I need to take the square root of 9. And if I take the square root of 9, I get 3. And I know a square root can be represented as 1 over 9. It's a rational, meaning fraction. It's a rational exponent. Square root is the same as 1/2. So if you say the square root of x, know that it's the same or equivalent to x raised to the 1/2. The square root of 9 is 3. But here's the deal. Notice that 9 and 3 are at different levels. 3 is in the numerator position and 9 is in the denominator. So I need to be able to account for them being at different levels. I need to take the 3, push up to the top. And that's why it is negative. Please go into the chat, give me a thumbs up, a thumbs down if that makes sense to you or if it seems rather confusing. Let's look now at numbers 3 and numbers 4. Okay, so I have log base 2 of x minus 1 equals log base 2 of 5. Notice that the bases are exactly the same. That has to occur, and at this level it will, but I want you to recognize when the bases of the logs are exactly the same, and there's no additional numbers. It's not like plus 5 over here, minus 7, right? Yes, there's a subtract 1, but it's in parentheses. It belongs to the value behind the base. When this occurs, the shortcut is we get to cancel out the log base. It doesn't have to be log base 2. These just have to be the same bases. It can be log base e, log base 10, log base 25. I bring down what was directly behind, in this case log base 2, and I have x minus 1 equals 5, and now I solve. X equals 6. But then you have to check for extraneous solutions. And extraneous solutions mean, hey, you got an answer, but if you plug it back in, does it still work? 6 minus 1 is 5, so log base 2 of 5 equals log base 2 of 5. This works. So x equals 6. And here, x equals negative 1/2. I guess I did not write it up here. And yes, you would have to be able to show your work as I showed earlier. I do want to reference the positions here. So we have a base, we have the value behind, and we have the exponent. Remember, it's this raised to this value equals this. These two values right here will never be negative. They are never negative. If you didn't know that, you do want to write that down. I believe there's a question in your test where they're going to try to trick you. These two values are never, ever negative. They can be fractions and decimals, but they can never be negative. Okay, let's look on right now to number 4. If I just rotate this, number 4. Log base 9 of x equals 5/2. So I'm going to write this in exponential form. That means the 9, the base will remain the base. I'm going to go across the equal sign and grab this value and write it as an exponent, and then I go backwards equals x. Now, if you don't remember this from the videos, it says that whenever you have a rational exponent, rational just means fraction. So whenever you have a fraction as an exponent, we have to rewrite this. So 9, we're going to take 1 over whatever the bottom number is. It doesn't matter what that number is. In this case, it's a 2. We write 1 over it. So first I need to take care of the bottom number, and then I apply the top number of the fraction every single time. Doesn't matter which one is a smaller number, like 5 is larger than 2. Doesn't matter that at all. It's always going to be 1 over the bottom number first, and then we'll take care of, in this case, the 5 afterwards. Remember, I just spoke on the half that whenever we have 1/2 as an exponent, it means a square root. So the square root of 9 is just 3. So I have 3 on the inside. And now I need to take 3 to the 5th power. You do need to be able to show work like this. So you can't just plug this into your calculator, come up with an answer, and then I'm going to go, oh, they understand the answer. You do need to be able to show all these steps. So what is 3 to the 5th power? Okay, so 3 times 3 is 9. 3 times 3 is 9, and then times 3. 9 times 9 is 81. 81 times 3 is 243. Now, I would be fine with you at this point going, okay, 3 to the 5th power is 243, right? But I need to see the steps that you use to achieve this. So if you only got to this part and you wrote down x equals 243, I would not provide you credit. I do need to see the breakdown here. So going to 5 and 6 and zooming it in so people at home can see. Anthony, I will upload this for you. There's no reason that you have to find a copier for it, but you just need to know how to do the problems. I know you weren't there with us in person on Friday. Okay, let's look at number 5 and let's look at number 6. So number 5 and number 6, we want to solve for x in number 5. ln is just a shortcut method. Like we have shortcuts on our phones and on the keyboards on our computers. ln is a shortcut. It means natural log, but ln is equivalent to log base e. This is the exact same thing as this. So I'm going to translate it into log base e. You don't have to, but I find for most students, they understand it a little better when they do that. Okay, well, this exponent comes in front, and we have 4 times log base e of e equals x. So I'm going to do some mental math here. E raised to what exponent equals e? So like we could even think of this as a 5. 5 raised to what equals 5? 4 raised to what equals 4? Whenever the base is the exact same as the number behind it, these are exactly equivalent. A lot of students think they just cancel out because that's what it appears to be, but they always are going to simplify into 1. So this simplifies to 1, and I get x equals 4. That is the correct answer for number 5. Let's take a look right now at number 6. Number 6. I went over this just a little bit ago, so I have log base 2 of negative 8 equals x. I'm not even going to go any further. This number and this number have to always be positive. And if they're not, you can't do it. So this is none. What is the answer? There's none. Or maybe you want to write it's undefined. Let's look right now at number 7 and number 8. Number 7 and number 8. Okay, let's solve for x here. Again, I'm going to rewrite this as log base e. Log base e, and then I'm going to put everything down. E raised to the 3x plus 4 equals x. Just like I explained in number 5, I'm going to take the exponent, the expression that's in the exponent, and I'm going to bring it down in front. So 3x plus 4 times log base e of e. Whenever this value for a log is exactly the same as what's behind it, it will always simplify to 1. And I know 1 times 3x plus 4 is simply 3x plus 4. Now we need to solve for x. So I need to move the x's to one side and then the values without the x to the other side. I'm going to move 3x over. So 4 equals negative 2x divided by negative 2, and I get x equals negative 2. Let's make sure this works. So I need to plug it back in and make sure it works. That's how we check for extraneous solutions. Okay, so I'm going to plug negative 2 back into this problem just to ensure that this does work. Remember that we have log base e of 3x plus 4. So if I come back up here and simply plug in a negative 2, I know log base e of e is 1, and then I take this expression that's in the exponent position and just move it down. So I want to know, does the left side equal the right side? This equals 1. 1 times this quantity is just 3x plus 4. Does this side equal this side? Let's check. 3 times negative 2, because that's what I was able to achieve when I solved, plus 4. Does this in fact equal negative 2? It does. So this correct answer for number 7 is x equals negative 2. Make sure you show all of your work on your test. Let's go on right now to number 8. So in number 8, the sole reason why we learn about logs is when we have a variable in an exponent position, it's impossible to solve unless we could do mental math. Like I'm giving you an example here. This is the common example I've used throughout the chapter. Oops, sorry. If I gave you this, you would all know, okay, 3 raised to what equals 9? 3 squared is 9. You'd go x equals 2. So if it's as simple as that, we just can do mental math. But what about when we get something like this? E is no longer in your math period. E is no longer thought of as a variable if you once thought E could be a variable. Just like I is no longer a variable in your mind. I is related to being a complex number. It's imaginary. And E is Euler's number. E is often sought. You can find it in real life matters when they're able to take and model really large numbers that are using E. So if we need to solve right now for x, and I have no idea, e raised to the what equals x, I have no idea. Let's go ahead and let's do this. So I need to remove the e so I can solve for x. So I take whatever this number is, because e is a number, and I do log base that number on both sides. So if this was a 5, it'd be log base 5 and log base 5, and then I bring everything else down. E raised to the x equals 7. So as I told you, whatever the exponent is, it slips right in front every time, and I have log base e of e equals log base e of 7. This doesn't just cancel out. It actually simplifies to 1, and 1 times x is just x. So I have log base e of 7. Now I'm going to grab a calculator, and we can replace log base e if we want with ln. So I could do ln of 7 if that's what I wish. I could do ln of 7, or I could do, if I forgot that, I could hit math because the base is not 10. I would type in my e raised to the 7. We get the exact, oops, sorry, put it in the wrong position there. There we go. We get the exact same answer. Now let's round here to the nearest thousands. I will make sure that any problem that has a decimal answer that's not terminating, so it's irrational, I will make sure to tell you in advance what I want you to round it to. Let's round this, in fact, let's round this to the nearest thousand. So I'm going to have x equals, let me move this down, we have x equals 1.94, and we can't say 5 because it bumps up 0.6. Let me grab a new piece of paper, throw this one weight in the basket. And let's move on right now to number 9. Number 9. Round to 3 decimal places. So a lot of students go, okay, here we have equations, but here we have equation, there's no equation here. So when you don't have an equal sign, think of it as equal comes after this number. So I'm going to write log base 2 of 6. There's no equals. I don't know what the answer is. So I'm going to write this in exponential form. 2 raised to, I don't know, equals 6. And now I'm going to see, can I do mental math? A common mistake is students think 2 times 3 is 6. Yes, 2 times 3 is 6, but that's not how exponents work. This means 2 times itself, how many times equals 6. So 2 times 2 is 4. That's not big enough. 2 times 2 times 2, that's 2 to the third, is 8. So I know that my value here is somewhere between a 2 and a 3, but it's not in a nice, pretty natural number or whole number. So what I'm going to do is I need to use logs then. I need to figure out what this is. And so if we want to turn this into an x, if that makes you feel more comfortable, feel free to do that. I'm going to do log base whatever this value, so log base 2 on both sides. The x comes down in front, and I have x times log base 2 of 2 equals log base 2 of 6. Again, this doesn't just disappear. It does turn into a 1. It simplifies into a 1, and 1 times x is x. Now, I'm going to grab a calculator, and because the base is not 10, I need to hit math, go up 3 places, and the base is 2, the number behind it is 6. And now it says to round to the nearest, 3 places over, so that would be to the nearest thousands. And we would have 2.585. 2.585. Let's look right now at number 10. Number 10. This is a great example again. I need to solve this, and this shows us why we have logs. Otherwise, there's no purpose of us learning logs, and in the next unit, learning all about the properties of logs, how you can expand and contract things. Logs are for situations when you have a variable in the exponent position, and you can't do mental math to get the exact answer. So 6 to the first, I know, is 6. 6 squared is 36, but notice 30 is like right here. So it's 1 point something, but it can't quite be 2 because 2 would be up to 36. I want an exact answer. How do we do this? I want to remove this 6. So log base 6, log base 6. The x drops down in front. I know this value is the same as 1. I'm going to be kind of lazy there. Log base 6 of 30. This multiplies, and now this is what I'm going to plug in. Math, go up 3 times. My base is 6. The number behind it is 30. And I have, rounded 3 places over, I have 1.898. 1.898. Let's do 2 more here before we take a break in this video, since 1 through 12 are very similar. Okay, so I'm going to put this into an exponential form. So when I do that, I'm looking for number 11. The base remains the base. We go across the equal sign and grab this value, or in this case, this variable. This becomes the exponent, and then we go back, equals 4. Equals 4. Okay, so the same thing we're thinking about. I'm like, 8 to the first is 8. 8 to the first, I got a little boy here, sorry, that's in the room. Benny, I'm not done yet, please. Okay. There's only 1 more left. Okay, give me 1 second, kiddo. Okay, let's look back at this problem here. So if I go, okay, I know 8 to the 0 power, where anything to the 0 power is 1. I'm just trying to come up with a way for me to see, could I do mental math? Okay, and then 8 to the first power is 8, but I'm looking for an answer of 4. And so I know it's not going to be a nice whole number, and I will need to get an exact answer. I want to remove this value so x is by itself on the left-hand side. Log base 8, log base 8, and this comes in front, so I have x times log base 8 of 8. I know this value is equivalent to 1. It doesn't just disappear, and 1 times x is x. Now, log base 8 of 4, I'm going to use a calculator. Whenever the base of the log is anything other than 10, I'm going to hit math, go up 3 times. The base in this case was 8. I want to make sure I'm plugging this in right. The number behind it was 4. And if we round 4 places, oh, I recognize this as being a fraction that I'm accustomed to seeing. So whenever you can predict whenever you're able to predict a decimal, it's an ongoing decimal, but you can consistently see the pattern and predict it, we can turn it back into a fraction. Hit math, press enter twice, and we can see it's equivalent to 2/3. Let's look right now at number 12. I want to find the inverse of this. Oh, okay, here we go. So with inverses, we want to switch our x and y. F of x is the same as y. So if you want to start by switching f of x to y, you can do that. And I do need to see all of your steps here. So I'm going to switch x and y. And now my goal is to isolate the y. I want to see y equals again. Let's make sure that I've written this correctly. This is a 2, 4, and 3. Okay, so I need to remove this 3 so I can eventually bring this down. I need to remove this 3 so this can come down, and then I'll add 4 and divide by 2, and then y will be all by itself. That's my thought, right? By the way, if you are somebody who thinks like, Ms. Bradley, I'm sorry, but I don't even know what inverses are. I know we do this term and we talk about inverses, but what does it really mean? Let me just show you a quick example, making something very, very simple so you understand. If I gave you a really simple linear equation that you would have seen in 8th, 9th grade, let's go with y equals x plus 2. And I said, okay, let's come up with what we can plug in and then what we get for outputs. What's our inputs? What is the input? And what is the output? Okay, so if I input 1 plus 2, I'd get an output of 3. If I input 2 plus 2, I get an output of 4. If I input 3, I get an output of 5. Okay, now let's figure out what is the inverse of this. This will be very simple math. So I switch the x and y. I subtract 2 and I get x minus 2 equals y. This is the inverse. And we are able to denote the inverse by putting a little -1 next to the same function. Now, let's try the exact same thing. But this time, let's plug in the output for input in this newly created equation. 3. 3 minus 2 is 1. And watch, it just reverses it backwards. It maps it backwards. I plug in 4. 4 minus 2 is 2. It maps it backwards. And 5 minus 2 is 3. So inverses allow us to just reverse. We're just going to reverse course. Whatever I have for the initial function, and inverse, if I correctly am able to calculate it using the procedures, we just reverse back whatever our input and output, they just reverse track. So let's go back up here. I want to solve for y. I'm going to do log base 3 because it's the 3 that I'm trying to get rid of. And then I put everything else down. And now whatever is the exponent pops in front, even if it's an expression, in this case, such as 2y minus 4. And this is log base 3 of 3 equals log base 3 of x. Okay? Now, we know log base 3 of 3 is simply 1, right? When these numbers are exactly the same behind the log, it doesn't just disappear, it turns into 1. And now my whole goal is to isolate the y. So I'm going to take this value and I'm going to add 4 to it. I know this is ugly, but I'm going to come up here. I have log base 3 of x. That's one quantity. And I'm going to add 4 behind this. I do not want you to mistake that the 4 gets added onto the value of x. I first equate this and then add 4. And now to solve for y, the next thing is I divide by 2. And then I divide this entire quantity by 2. So if I come back up here, I could write the inverse of this would be log base 3 of x, that's one thing, plus 4, and I divide the entire thing by 2. And it would work the exact same way that linear did. So if I came to the original function, which is right here, and I came up with values, and I came up with values here, and I can demonstrate that. Let's just plug in something like 1. Let's just make it really, really simple. Let's do 1 time. So if I plug in 1, I'd have 3 raised to the 2 times 1 minus 4. Okay. That would be, if I wanted to be really lazy here, it'd be 3 raised to the, well, 2 times 1 is 2, and 2 minus 4 gives us an answer of 0.1111, right? Okay, simple enough here. Now, if I come here, so I'm going to turn this into a fraction, by the way, because I'm able to see a pattern, and I get 1/9. Easy enough. Now watch this. I'm going to take this function and I'm going to reverse it. So I inputted this into the original function, and this is what I got. When I take the inverse, if I input in what used to be the output, so I want to plug 1/9 in here, do all the math, and I better come up with 1. it proves to me that it works. So I'm going to do log, and now because, oops, this is log base 10, I need to hit math, go up, I'm going to plug in base 3, and the number behind it I want to plug in is 1/9. I'm going to get an answer here, and then I'm going to add 4, and then I'm going to divide by 2, and I get an answer of 1. I just proved to myself that I correctly was able to identify the inverse.